In my many years of teaching this course, I've heard a great many complaints, but the most common one is that this subject gives me a headache. And, there's a couple of commonly suggested remedies for that you can pick up over the counter at your local pharmacy. The first is the old standby. This is aspirin, acetyl salicylic acid. A very old drug, but one that's still effective. Second is Tylenol, or more, this generic name is acetaminophen. Third, ibuprofen. The trade name on that was Advil. And finally, if those don't work for you, then you could always just try crack. Probably not the best of remedies, but, you're pretty much guaranteed not to remember the headache if you're high on crack. I don't recommend that one. The other three that you'll notice are all aromatic rings, for starters. You'll notice they all have specific substituents on them. They're all dye-substituted, and the orientation is critical. Now, for them to do their job and inhibit the enzyme that causes the inflammation that your body is interpreting as pain, they have to fit the enzyme properly, which means the orientation of the groups on the ring is critical. Now, these are all members of a class called the cyclooxygenase 2 inhibitors. They inhibit prostaglandin synthesis step, which causes inflammation. It also, for the ladies in the room, causes your menstrual cramping, and eventually is one of the same processes that's used to start the labor if you ever have a child. This process does have positive uses, but for our everyday life, it's sort of annoying to be blindsided by a headache caused by your professor. So any of these three would interfere with that. If we looked at the evolution of this, you would see that the structures are similar, but they're actually getting a little bit better and tighter fit for the enzyme. Aspirin for a lot of people isn't really a great headache remedy. For some people, Tylenol, for me for instance, Tylenol works really well for muscle cramping, but not so good for a headache. Ibuprofen, on the other hand, works great for a headache. So, it's where I begin if I have, a headache myself. Now that we know how to put quite a number of functional groups onto the ring, either directly or by a functional group interconversion, we have to look at what happens when we need that second group in place, the way that we did with all those previous examples. So what's going to happen here is that the first group we put in place is going to have two different effects we have to concern ourselves with. The first, the electronics of the ring. Is the ring going to be more or less reactive? Now, you can think about this as the ring being a donor. If it's got something attached to it that donates, well, then it's a little bit richer. It's more likely to be charitable and donate. Whereas if it has a serious drain on it, something that withdraws, then it's less likely to donate. And that's really what we're asking it to do in an electrophilic substitution reaction, is donate electrons to the electrophile. So we're going to have to think about that as part of our consideration. The other is the regiochemistry issue. Not just will it react, but where? If there's one group in place, there's 5 other positions on the ring. And if we consider symmetry, there are 3 other positions on the ring, the ortho, meta, and para. But there's got to be some degree of control here. We can't just have random mixtures. And in all honesty, there's not. There is control. There is a reason why things go where they go. In the second substitution reaction, it's directed by the first. So we're going to have 3 classes of substituents that we're going to deal with. Based on whether they activate the ring or deactivate it, and based on where they direct the incoming electrophile to go. The first of those classes are what we call the strong activators. These are generally groups that have a lone pair of electrons on them, or alkyl groups. Alkyl groups work by a slightly different mechanism. It's an inductive effect based off hyperconjugation. But the idea is the same. They donate electron density into the ring. So relative to benzene, they're more reactive. These are things like your OH, your SH, ethers, thioethers, some amines, although we have to be a little careful with that one, amides. So what we're going to see here, and the reasoning behind this, is that not just do they activate the ring, but they direct to the ortho and para positions. Now, from the beginning there, let's say we have a problem. They direct to the ortho and para, not or, and. We have a mixture. Ortho and para directors, of which many useful things that we're going to deal with will direct to those positions, by definition, electronically will give us a mixture. Now, we can deal with that in other ways, and we'll talk about that in a few minutes, but at first we have to look at it as giving us a mixture. And so let's have a look at why that would happen. What I have here is the generic, Z group with a lone pair on it. And if we look at that donating the lone pair into the ring by resonance, we'll see that the first resonance structure that I can draw from that actually has a negative charge on the ortho position. Remember that our electrophile coming in is very strongly positive, so guess where it's going to be attracted. If I keep drawing resonance structure here, what we'll see is that the next resonance movement of electrons ends me up with a negative charge on the para position. Hence the mixture. We have resonance that takes a negative charge between the ortho and para positions. So they're both electronically activated for the same reason at the same time. Notice what got skipped though. Nothing happened at the meta position. That's important, which means there's no reason to go there. The plus charge on the electrophile is going to be attracted either to the negative charge on the ortho or the negative charge on the para. Now remember, these are just resonance structures. They don't really exist, but it's a good explanation. And I think it's a little bit better than what your textbook uses. Your textbook does the addition and then explains it by resonance. I think you need to think about that beforehand. Like, why does it go there? Not after the fact. So the overall picture looks like this. You can see the partial charges on the ortho and para positions, not on the meta. And so that's where we're going to end up with our substitution with this class. Now, along with this, there's a second class, which are also ortho-para directors, but they deactivate the ring relative to benzene. And these are basically the halogens, fluorine, chlorine, bromine, iodine. They're electron donors because they have lone pairs, but they're very electronegative. So they're withdrawing from the ring inductively. They're more electronegative than carbon, significantly more. So you get this sort of mixed effect where they still direct to the same spots, but they slow down the reaction relative to benzene. So that causes us a little bit of trouble here and there, but we can live with that. The resonance structures are exactly the same, but the only change is that the inductive effect, which does not go through the pi system, goes through the sigma bonds instead, is more pronounced at the ortho position. So compared to something like a methyl group or an alcohol, what you'll see is that the halogens are sort of less favorable towards ortho substitution, and that's really just about the inductive effect being stronger the closer you get. Resonance is transmitted through the pi system, so it doesn't really matter. The ortho and para are essentially identical there electronically, but the ortho position gets more of the inductive effect, so that's what's going to get decreased somewhat depending on which halogen we're working with. That's a finer point. Your book has a nice table to explain it, but it is something to keep in mind for later. All right, the third class that we're going to have of our substituents are strong deactivators for the ring. Now, these are things that either have a cation directly attached to the ring or, and most commonly, have a pi bond system where the outer atom, what I have here denoted as Y, is more electronegative than the inner one, what I have denoted here as X. And what that means is that resonance will occur out of the ring, not into it. The complete opposite of what we saw for the donators. And if you notice, what happens there is if we draw our first resonance structure of resonance out of the ring, we end up not with a negative charge on the ortho position, but with a positive charge on it. So think about it. Now we're looking at not attracting the electrophile to the ortho position, but repelling it away from the ortho position. As before, the next resonance structure involves the para position in the same electronic sense. So we end up with a positive charge there in resonance, not attractive to the electrophile. So I jokingly say that there's no such thing as a meta-director. There's an ortho and para undirector. We're not making the meta position attractive in the way that we made the ortho and para ones in the previous example. We're actually making the ortho and para positions unattractive. So by comparison, meta looks good. So the old joke of dating, if you want to look hot, get some ugly friends.
kind of works here for the electronics. That the ortho and para positions are so unattractive that if anything happens at all, it'll happen at the meta position. The other thing to keep in mind here is that these deactivate the ring so strongly, they do actually introduce some problems, particularly with the Friedel-Crafts. This is the one big limitation. The Friedel-Crafts alkylation, the Friedel-Crafts acylation, the carbon cations cannot handle a ring that has one of these groups on it. So it does effectively kill the Friedel-Crafts reaction from occurring. So this is something that we really have to keep in mind as we plan out a synthesis, that if we put one of these groups in place and don't modify it into something electronically different, as we did with the functional group interconversions, then we cannot attach a carbon functional group directly by Friedel-Crafts mechanism afterwards at all, period.
As I mentioned earlier, the problem that we're going to have with an ortho and para director is that by nature you get a mixture out of it. You get ortho and para, and there's no real way to avoid that. But with a little forethought, maybe we can control it. So I'm going to show you two ways that exist that we can sort of plan our synthesis around some degree of control. The first of those involves the size of the group that is present. Now, depending on what you're doing, you may have some ability to switch out one group for another, and that's the assumption with this particular example, is that you could change out one alkyl group for another. Perhaps this is a precursor to an oxidation or something, which we'll talk about a little bit later. So what you see here is the nitration of an alkyl benzene. And as before, you get an ortho and a para. Now keep in mind there are two ortho spots and one para one, so statistically we would expect twice as much ortho substitution as we would get for para. And in fact, if the R group here is a methyl group, that's almost exactly what we see with a 58 to 37 ratio. It's pretty close to statistical. What that tells us is that a methyl group has very little effect on the incoming group. It's not big enough to really block out the ortho carbons significantly. But you can also say, well, the ortho carbon is very close to this R group, so as we take up that size, we might expect to get less ortho substitution. So look at what happens when we add one additional carbon to the mix. If we make it an alpha group instead of a methyl, we could still do a lot of the same reactions on that we might be interested in. Now we're up to a 1-to-1 ratio, so we've actually lost some ortho, gained some of the para isomer, and these numbers here, notice they don't add up to 100. These are actually the isolated yields. So this is what you're actually getting out of it at the end, not just the ratio, but this is the isolated product amounts. So what you see is that now we're getting there. You know, a little bit of a bigger steric presence for an ethyl group versus a methyl, and now we're starting to see some selectivity towards the para position. We take that one further carbon up to an isopropyl group, so adding a second methyl group to that carbon attached to the ring, and now we're looking at 2-to-1 in the opposite direction. We're looking at 62% para, and you know, that's, if you wanted a para substitution, you're getting close to real control here. And the last one, if we added yet another methyl group there, so now we have 3 methyls on the carbon attached to the ring. This is a T-butyl group. Now we're looking at, you know, about 5-to-1 selectivity for the para position. There are other ways to do this which are a little more advanced, but where you put in a group that's removable later to block out the ortho position. It's a little bit beyond what we're going to deal with in this particular chapter, but the idea is just that the more we bulk it up, the more things are going to go towards the para position. And if that's what we need, so much the better. If it's not, we're going to have to look at going at it a different way. We'll talk about that before the lecture is over. All right, the other consideration, which we really haven't talked about at all yet, is the size of our incoming group. Now, we dealt with this sort of problem with the substitution reactions back in part 1, where we had to deal with, you know, the electronics and size of the leaving group, the electronics and size of the nucleophile. We really haven't dealt with that here, but it is still a significant consideration. And the example used in this case is the electrophilic substitution of chlorobenzene. So a chloride, still relatively a small group, a little bit more of an electronic effect ortho because of inductive effects, as we talked about earlier, but still it's useful for comparison purposes. The first example, which we'll come back to in a moment, is to chlorinate that. So using the chlorine and iron chloride, and you notice what we see is a certain degree of paraselectivity. Now, again, the halogens are a bit of a loaded dice when it comes to ortho anyway, but we need a comparison point, and this is one that exists in the literature we can look at. Not really great selectivity, though. You know, I mean, this is better than statistical, but still, if you needed the para, you're still wasting an awful lot of material here. So if we look at the next one, the nitration conditions, you'll notice that's a bit cleaner. You know, now we're looking at like, 70%. That's not bad. And overall, what we see here, and the effect that's going on here, is that the nitrocation is actually a good bit larger than the incoming electrophile for chlorination. So that the size difference really is helping us control ortho versus para. Now we take that one step further up with the bromine and iron bromide. Again, the control's even better. So the larger group gives us the better control here. Now we're looking at almost a 9-to-1, selectivity for the para position. Now, some of these we could convert to other things. Now, essentially, chemically, what I could do with an aromatic chloride, I could probably do with a bromide. So that first and third example are an example of functional groups that would react similarly, so that it might be easier if I really needed the para one to make the bromide instead of a dichloro substituent, a dichloro substituted ring. The last one, and it's one we're going to put to use, is to look at the sulfonation. Now this is the largest of the electrophiles that we use regularly, aside from the alkyl groups, because that's much more variable, but this is the largest of the standard electrophiles, and look at the selectivity here, 99-to-1. This is almost exclusively para, and the reason for that is the sulfonate group, the sulfonic acid group as an electrophile coming in, the protonated SO3, that's our active electrophile, is a very large group. So it really does not want to be ortho to anything. And we're going to put that to use. That's a controlling factor, because as we talked about in the previous lecture, we can remove that. So we can put it in place, use it to block things, and then when we're done with it, flush it down the nearest toilet. Get rid of it. Take it off the ring, and it's done its job. Okay, so let's see that concept in action. If we wanted to make orthodichlorobenzene, and we began from chlorobenzene, we could do the direct chlorination. And what we get out of it is the mixture of ortho and para. The problem here is that the para is the preferred isomer. The ratio is like 55-39. So we're not getting a lot of what we want to begin with, and we have to do all the work to separate out that undesired isomer. On the other hand, if we take advantage of that sulfonate by starting again from chlorobenzene, but putting the sulfonic acid group in place first, it goes almost exclusively para, 99-to-1. Getting rid of a 1% impurity is usually not bad. It's usually pretty easy to do. Now look at what we have. The chlorine is an ortho and para director, so the para position is taken, it's directing to the ortho site. The sulfonic acid is a meta director, which is directing to the exact same spot. Meta to the sulfonic acid is ortho to the chlorine, so they're working together to put the next electrophile in exactly the same place. So if we do the chlorination now, we get exclusively the ortho dichloro isomer, and then we can easily remove the sulfonic acid group that helped us as a blocking group and as a directing group, a removable blocking and directing group. So it actually is more steps. The trade-off is you get the product you want as the major product instead of a minor one, and then a lot of work to do separation. So depending on the exact case that we're dealing with, we may have to work that trade-off of doing a longer synthesis to get a cleaner result, rather than doing something short that's messy. And it depends, of course, on the cost of the starting materials and how much labor you want to put into it and how difficult the separation is. But in some cases, in a purely thought experiment sense outside of the lab, it makes more sense to make the product you want, regardless of the number of steps, within reason, of course, than to have a mixture that's messy that has to be cleaned up. So it depends on the exact case which way you would take, but the thinking is something I want you to get experience with now, that sometimes it pays to do a longer, cleaner method than a short, dirty one. So let's go back and have a look at the example of aspirin. The only thing we're not going to talk about here, which I've shown in fuchsia, is the ester group. That is something that we're not going to deal with until we get to chapter 21, where we deal with carboxylic acid derivatives. The direct precursor for aspirin is salicylic acid. Now, the reason that ester group is there, and this was, I believe, by Bayer Pharmaceuticals, and it was the first of the blockbuster pharmaceuticals, came out in the late 1800s, and really probably the birth of the modern pharmaceutical industry, was that the salicylic acid has been used for several thousand years as an anti-inflammatory. It goes back in traditional Chinese medicine. It's the earliest known written prescriptive from Hippocrates in ancient Greece, who actually wrote that people with various maladies should chew on willow bark, which actually contains a large amount of salicylic acid. The problem with using that directly is that it actually burns the stomach lining pretty badly. It's very, very acidic, and so it causes digestive problems while it's curing the headache. So it's no longer used directly. It's used as a topical anti-inflammatory. So if you have problem skin, they may recommend something like a salicylic acid wash. A lot of current skin creams have that in it, along with benzoyl peroxide. But the idea is that by covering up that one alcohol group, the acidity went way down and the stomach toxicity largely went away. Not entirely. People who take too much aspirin still have problems with digestive ulcerations, but it made it usable by the larger public in a regular basis without becoming a significant toxin. So what I wanted to do was look at the salicylic acid synthesis, because that's an aromatic ring. It's one step away from aspirin. It is the natural precursor that aspirin's made from. Literally, we've actually made, some of you made aspirin in General Chem 1 lab. It's very simple. Essentially, you just mix this with an acetyl source, and you pull aspirin out at the end. So it's actually really, really basic chemistry to do that last final step and put on the acetate group. But dealing with the ring, you'll notice that it's ortho-substituted. And, so that's going to present some challenges for us. Let's look at it. The two questions we have whenever we're asked to make an aromatic ring system is, one, do we know how to put those groups in directly, or does it require derivation? In this case, neither of the two substituents is something that we can put in a single step. We have to do an oxidation to get to carboxylic acid, and we have to do a lot of work to get to an alcohol. Neither of those is a single, simple step to put those groups in place. The second question is the orientation of the groups and their relative directing ability. Now, they are ortho to each other, but if we look at them, they are not necessarily both ortho and para directors. We could oxidize a ketone, for instance, to the carboxylic acid. So if we look at that one as being a logical one step backwards from salicylic acid, we have an ortho and para director, which is the alcohol, and we have a carbonyl, which is a meta director. Now, since they're ortho to each other, that suggests that the alcohol is probably going to end up being the one that's there first. The point of analyzing the structure first is so that we know the orientation versus the directing ability, and we can rule out some pathways. We know that ketone's not going to be there first because it would give us meta substitution, which is not what we want. So we've gotten rid of one pathway without really working too hard at it. So we back up another step to the alcohol. Now, as before, we have a couple of different ways we can manage that. We can either start from a nitro group. The forward process would be to reduce that to the amino group and then diazetize it and treat it with water and some copper salts. Or we can start with the ketone and then treat that with Baeyer-Villiger conditions to do an oxygen insertion and then cleave off the ester. Either one of those ways would get us to phenol, and either one of those ways, just as directly, is only a single step from benzene. So this is the thought process. Going backwards logically one step at a time, we can work out the pathway that's the most reasonable. Occasionally we'll see some divergence in the pathway that will allow us to have a backup plan because, again, it's not always about what's chemically possible. Sometimes it's about what's affordable and what's available. So either one of those last two intermediates will get us to the product and also could be made from benzene directly. That's more of a thought experiment. We do that a lot with our introduction to aromatic reactions of having you make everything from benzene. The reality is no one in their right mind would ever do that. First of all, it's unnecessary. There are a lot of precursors that are available and easy to get at and cheap. And second, benzene is considerably more toxic than the other precursors we could use here. So let's look at a slightly different approach and we'll see where it takes us. If we started instead of benzene with toluene, which is just methylbenzene, it's a common organic solvent, relatively inexpensive, and a lot less carcinogenic than benzene, we can sort of think that this might be pretty easy to do. And we're going to use that same trick that we saw earlier with the size to block off the para positions so that we get ortho, because we saw that the methyl group wasn't particularly good at giving us ortho substitution. So we're going to use the sulfonic acid again to block the para position, since it goes there almost exclusively. And then we're almost there. Basically, you could think, well, if I did a Friedel-Crafts reaction here, then I've got one more step to just do the Baeyer-Villiger oxidation, put my OH in place, and I'm almost home. And there's a problem there. It doesn't work. Oh, the easy way doesn't work. You hate when that happens, but it does happen. The limitation here is that you cannot do a Friedel-Crafts reaction on anything that has a strong electron withdrawing group, like a sulfonic acid. So that's out. Can't do it. We're going to have to get the oxygen in place another way. Luckily, we can do that. It's longer, but it will work. We can do a nitration instead with nitric acid, sulfuric acid. That's going to give us the ortho-nitro compound. At that point, it probably makes sense to get rid of the sulfonic acid, although we could have waited till later to do that. Then we're going to take the nitro group, reduce it to the amine, and as we talked about in the functional group interconversion lecture, we can diazotize that and, using water as an incoming group, replace that N2 cation with an OH, make a phenol out of it. So now, if you look at this, we now have an ortho carbon next to our hydroxy group, so all we have to do is get that to be a carboxylic acid and we're home. And that's actually relatively easy to do. That just requires a permanganate oxidation. As we talked about in that other lecture, anything benzylic that has a hydrogen on it, a carbon with one hydrogen or an oxygen, will oxidize very easily to the benzoic acid. And so that's what we're doing here. So we're now home. We actually got salicylic acid out of this from a pathway that's a lot different. Now, the reason I showed you this one is that not necessarily that I would ask you this on exam, but that in a lab, things are a little different. You wouldn't want to handle benzene if you didn't have to. It's not horribly deadly or anything. It's not like handling, hydrogen cyanide gas or something, but it's still something that long-term exposure would be bad. And also, particularly in industry, where you're talking about a reaction flask the size of a small building, you certainly don't want to be dealing with strong carcinogens on that scale if you don't have to, because then you have one leak and you have a serious health concern on your hands for that that area. So if avoidable, then you would avoid it, and this is a way you could. So what I want you to take from this is there are multiple ways to get to some complex products, and some of them will differ not necessarily in feasibility, but in cost and in safety.